Okay, so I've just finished recording the lesson on, or at least our first lesson on determinants. I don't have a ton to say in terms of like calculation here, or at least in this Sage module, but I do want to show you something in a moment. So if you click on the Sage module for this lesson, all I have here is the syntax necessary to calculate the determinant of a matrix. So the syntax here is just a.det if you define your matrix. So the predefined code here I have just gives you a random matrix and then calculates its determinant. So if you click evaluate here, here I'm choosing a random 10 by 10 matrix, and then the Sage will calculate the determinant for us. So of course we could do this ourselves by changing this matrix to be anything we want. So I don't know, if I just fill this up with maybe this 2 by 2 with some numbers, I can reevaluate the code. The matrix prints out, and then it tells us the determinant. This is a 2 by 2. So we could just check that this makes sense. We should get 5 minus -7 times 2. So that's what 5 plus 14, which is 19. So please use this to calculate your determinants. And one thing I want to point out is that even when we had this let's see here. Let's do a random matrix filled with integers. I'm going to do a 9 by 9 here. When I click evaluate, the code runs fairly quickly. This is pretty quick code. And I just want us to think for a moment about whoever wrote this code. What are the internals here? What did they do? And I want to argue that they probably didn't use the definition of determinants. Because the definition is recursive, and for this 9 by 9, you would need 9 8 by 8 determinants, and each of those 9 8 by 8s needs 8 7 by 7s, and each of those 8 7 by 7s needs 7 6 by 6s, and you get just this terrible mess of determinants. I actually prepared a demo here to sort of show you how terrible this could be. So this is just on my computer. This is just terrible code that I wrote to illustrate a point. You don't need to understand anything I'm writing here. I just want to make a point. So for those of you familiar with Python, I've written a function here called bad_det. And what this function does is it basically just uses the definition of a determinant to calculate a determinant. So this is dropping down the first column of our matrix and then summing up a bunch of terms where we delete rows and columns and scale everything appropriately and then add more determinants. And I want to show you how bad this is from a computational point of view. So I'm going to define a random 9 by 9 matrix here in my terminal. So here we have a random 9 by 9 matrix. And now what I'm going to do is I'm going to time the code that I just wrote. So I'm going to apply my function bad_det of A, and I just want to see how long it takes my computer to do it. So I'm going to hit enter, and let's see what happens. Go. So we're waiting. We're waiting. Okay, great. So the code ran, but it looks like it took about 7 seconds for my computer to calculate the determinant of this 9 by 9 matrix using the definition, which I wrote in a function bad_det. I want to now do the same calculation, but instead of using my terrible function, I'm going to use the built-in a.det, which is the code built into Sage. So this is the same determinant calculation, just with hopefully better code, and let's see how long this takes. It's nearly instant. The code runs almost instantaneously. So this took, I don't even know, is this a microsecond? It went really, really fast, whereas the code I wrote took 7 seconds. So this is kind of remarkable. And you'll even see here, if I run bad_det on A again, it's going to take 7 seconds or whatever. But we will get an output. So we get this output. It's a large number, 105,77030. We can check that we get the same answer as we do if we run the well-written code, except we get it almost instantaneously. what's happening here on the back end is that whoever wrote this code is using PA equals LU in some fashion. So instead of doing this terrible determinant formula, they're quickly row reducing the matrix and then multiplying by all the diagonal entries you get when you do all those row reductions. The computer can do those row reductions much faster than it can apply the recursive definition of the determinant formula. So lots of times when people use determinants to solve a problem involving a large matrix, I'm almost immediately skeptical of whether or not they need the determinant, because it's very likely that the problem they're trying to solve requires row reductions anyway, or could be solved with row reductions. And by using a determinant, you're probably doing those row reductions anyway. So this is one of those situations where we have the definition of a determinant, but the actual calculations involve us having to use the theory as we've described it in the lesson. So that's one of my, I don't know, I like seeing that a lot because it really does illustrate the point that writing good code matters for one, but also just because we have a definition doesn't mean it's the right thing to use when we want to calculate something.